So now let's get into some problems that are in 7.1. Not specific homework problems, but just in general problems that I feel can help you out with understanding everything. The first thing that we want to make sure that we talk about is notation. And so as was mentioned in the overview or possibly in the PowerPoint slides that you viewed, you saw it there, that we're going to be needing to establish confidence intervals by doing something very specific. We're going to need to get our sample value. And so when we're in 7.1, they're going to come with a very familiar setting, and that is percentages or proportions. So we want you to know that proportion is 100% the same as percentage. Right? And so they're going to use those words interchangeably, but a confidence interval for the proportion is the same as the percentage. Essentially, if the percentage is 40%, the corresponding proportion is 0.40, right? So the proportion is basically just the decimal equivalent of the percentage. So as you hear those words, I didn't want that to confuse you. Notation wise, we're going to use the symbol p hat, p with the little party hat on it, to be the sample proportion. So this will always be either straight out given in our problem, or we'll have to do a quick division to find it out. You'll see in the homework problems, I think most of the time they make you divide two numbers in order to come up with the sample proportion. They'll usually round this if they have to do the division the same way we do it for uh, probability, and that is to round to 3 significant digits. Okay, so if you have to do that division. But from a standpoint of notation, p hat is the sample proportion. P without the hat is the population proportion. This is what we're trying to estimate, right? This is what we're getting a confidence interval for, is this population proportion. And so every time it's going to be the same. We are going to take a p hat and add and subtract an error to it in order to get some bounds for p. So one of the bounds would be p hat minus the error, and the other bound will be p hat plus an error. You're doing this in every single problem, actually in both of the next two sections. This section is going to focus on proportions. The next section is going to focus on means. The symbols will be different, but the idea is the same. Hey, this is the p hat's the best that you can predict with your sample. It's got some error. Apply that error to get a range of values where you are pretty confident, right? And you'll be able to name the level of confidence that P exists. And so that's our main goal. And so what's going to happen is they're going to have some problems, and you'll notice that P hat's given. So maybe it will say something like this. We surveyed 100 Folsom Lake College students and found that 10% did not have internet access at home, right, for various reasons. So that's what we have. That's some data that we went out and got. And so what I wanted to show you is that we already know our sample percentage. It's 10%. That's what came out of the sample. There's about 9,000 students at FLC, so 100 is definitely a sample. And they're going to ask a question like this. Find the 99% confidence interval estimate for the true proportion of all FLC students who don't have internet access at home. That's what a typical question is going to look like. Okay. And so how do we do this? How are we going to find out that confidence interval? A confidence interval is going to involve a few things. It's going to take our best guess, which is the 10%, and it's going to add and subtract an error. So this number, this 10% number, is either going to be given to us like it is in this problem, or they may have said we surveyed 100 FLC students and found that 10 of them did not have internet access. Then we'd have to divide the 10 and the 100 to get the same 10%. Now for the error, that's where the formula is going to come into play. The formula for the error when you're dealing with proportion should scream to you, I'm the one. Now here's what it looks like. The notations are pretty strange at first. It looks like this, z alpha over 2. Now that's one notation for a single number, and we'll talk about that, times the square root of p hat q hat all over n. So that might look a little bit daunting, but we don't want it to be. As we take a look at some of these symbols, there's some that we know. E is what we're trying to find, so we're not going to be able to put anything in there for that. But take a look at what's under here. P hat. If you remember from our notation, I'm just going to scroll up. P hat is the sample proportion. It's what came out of the sample. And so what came out of the sample was 10%. So our P hat is 10%. And I don't know if you remember Q very well, but Q was introduced to us when we were dealing with the 5.2 area, finding the binomial. So Q hat is simply 1 minus P hat. It's the opposite of P. And so if P hat is, in our problem, 10%, then Q hat is going to be 90%. And so this P and Q are linked that way. They have to add up to be 100. And so if it's 10% that was in the sample, it's 90% that were not. 10% that said they had did not have internet access, and 90% that said that they do. And then we put it over n. Now n's pretty easy as well. So with just the information that was given in the problem, look at how much we were able to fill in. We know it's 10% plus or minus an error, so we know how to finish. We know when we go to the error formula, we're going to choose the only ones with p's and q's in it when we're dealing with the proportion, right? So if we're getting a proportion, you're going to go to the only error formula you'll ever see with p's and q's in it. And we're there. So the only thing left to do is find out what this z alpha over 2 is. Now, I'll show you how to do that in a different problem. But the z alpha over 2 for 99% is going to be 2.575. So if I could get you to easily look up that, and it is an easy lookup, then you'll be set. So I'm going to do that in a different video, show you how to find the z alpha over 2's. But this is what's there. You use this formula, you quickly drop in the numbers for p hat, q hat, and n because they're given, and then you go to the chart. Now what chart would you go to? You go to the z chart to look that up, and we get a corresponding number of 2.575. Now let's run that error formula. That is going to be 2.575 times the square root, and be careful not to cut your square root off, 0.1 times 0.9 divided by 100 is all there, and I hit equals, and here's the number that's displayed, 0.07725. So I have an error of about maybe I'll just say error is equal to 0.077. Don't get too caught up with the rounding there. So the only thing left to do to finish my problem is to take this error and add and subtract it to the 0.10, because I knew that 0.10 wasn't perfect, and I just found out the error was about 7%, which is pretty high. And so we take our 0.10 and subtract away the 0.077 and come up with the 0.023. And if I add the 0.077, I get 0.177. So the true proportion P lies somewhere between 0.023 and 0.177, or the sample percentage of those that don't have internet access at home could be anywhere between 2.3% and 17.7%. So, how do we write this as a sentence? We are, and remember what our confidence level was. It was 99%, right? I'm using that 99% to come up with that 2.575, so it is playing a role. We are 99% confident that the true percentage, or let me put proportion, of FLC students who don't have internet access at home is somewhere between, and then you're just going to copy those numbers, 0.023 and 0.177. You could put those as percentages as well, but I chose to just use the word proportion, and so I should technically then put them out to be decimals. But we don't know what the true percentage of students that don't have internet access are, but we do know that it's somewhere between, at least we're 99% confident, that it's somewhere between 17.7%, like it's no higher than that, and it's no lower than 2.3%. It's somewhere in that big window. That's the idea of what to do. So in the following videos, I'll tell you, hey, how did I get this 2.575 number?